Thank you. It's a pleasure to be here. So Nilsen-Thurston theory, I take it as foundational for starting to understand mapping class groups. So what I'm telling is not at all a new tale, and there's a lot of really good references out there. But for the goal of this mini course is to give you some flavor of the ideas and the tools that go into this sort of starting point for understanding mapping classes. So I'm going to start with a definition of those. All right. So some introductory stuff on elements of mapping class groups. S is going to be a surface, and it's oriented so that I can talk about the group of maps from the surface to itself, which are orientation-preserving homeomorphisms. But I don't care if I isotope or push these maps around a little, so I'll have a equivalence relation. I identify two maps if they're isotopic, same thing as modding out by the subgroup of those that are isotopic to the identity. So this way what I get, I didn't write. I get a discrete group known as a mapping class group. Let's draw some examples of elements of mapping classes, elements of this group for every surface. So some of the obvious things that can happen is if you have a symmetry of the surface, then you can see a mapping class right away. Draw the genus first before the actual surface. Here's something that you imagine could be order 3. Remember, I don't care if it's wobbly. These are equivalence classes up to isotopy. Here, if you skewer them in the middle and flip it over 180, you've got an involution there. That's a useful one. Let's see. So these are finite order here. What's the first example of an infinite order one? These are Dane twists. What do those look like? Well, here's a surface, and I imagine a simple closed curve on the surface. For example, here's one here, and if I zoom in there, this mapping class has a small support, so this is just this arm right here. I see, call this T, and what's going to happen is it's only the support's only going to be in an annular neighborhood of this core curve, and what it looks like is not going to change the core curve, but any other curve that comes through it. This is before the Dane twist, true to its name, twists around it. So that's one Dane twist around that curve. So that's your simplest infinite order mapping class. Another relevant example of mapping classes are actually braids. So if you think of the braids, a braid on n strands, as a permutation, as an isotopy, sorry, of these n punctures on a sphere, well, this is the mapping class group of, by this I mean the puncture disk. So these also, braids are a special case of mapping class groups. And relative to what I've already described, a nice, fun exercise to, if you haven't thought about it, there's this taking the quotient by involution like this. I think I've seen it called the Berman-Hilden cover. Let's see. You'll get a branch surface, and the branch points you can think of as mark points. Let's see. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And if I take, say a Dane twist about one of these curves that's fixed by this involution, that's going to descend to the quotient below. 1, 2, 3. And what it descends to is the braid that swaps these 2 points. So that's a fun thing to draw for yourself and work out if you want an example to toy with. Okay, so these are some basic examples. Now, the first full mapping class group that's familiar because it sort of shows how the mapping class group is an intersection of lots of different contexts. Oh, let's look a little bit more at the entire mapping class group of the torus, which turns out to be nothing more than SL. I'll write it like this. 2Z. Okay, so why is that? Why are they the same thing? So here's the torus, and then I'm going to carry around some color. And of course, the torus has its cover. I can just imagine this is the unit torus, so it's covered by R2. And there are, I can pick two curves that intersect once. Oh, that might confuse me, because I never colored that guy red. Sorry about that. All right. So this one goes around that way, and this guy goes this way. All right, these are going to lift to things that repeat here. So I can, up to isotopy, I can imagine that all my mapping classes fix this point of intersection here. In the cover, they're fixing the integer lattice. And I can call this curve right here, from its place in R2, the 1, 0 curve. And I can call this one the 0, 1 curve. And what you'll see, so you've probably thought about curves in the torus this way before. So the simple closed curves, that's what I always mean when I say curves. The simple closed curves on the torus exactly correspond to these vectors PQ, except for 0, 0, which record how many times they wind around one curve, which I say is the longitude, and the other curve, which say is the meridian. The two basis curves that intersect once. So because curves correspond exactly to these two, and also because if you look at where a mapping class takes these curves, what's left is just a disk. So, and up to our equivalence, up to isotopy, there's only one way to glue it in a disk. So a mapping class of the torus is entirely determined by where it sends these two curves. So where it sends the basis curves. So that puts it in a corresponding matrix in SL2Z. Okay, this is a very, very simple, very useful and actually suggestive example. So let's actually think a little bit about what we know about elements of this. So mapping class group gets its terminology, this being called the modular group. That's the Teichmüller modular group sometimes. There's really three kinds of behaviors for elements in SL2Z. And they're going to correspond to three kinds of behavior of mapping classes. And where I'm going next is Nilsen-Tёrstona theory is a deep generalization of this simple picture that you're familiar with, most likely here. All right. So let's remember what happens for these kind of matrices. Well, in the case that they're elliptic, then because they're in SL2Z, then they're actually rotations, and in particular, they're finite order. For example, here's one. I want that one. Okay, and you can actually figure them out directly from the matrix by looking at the trace. This is the trace being 0 or 1. Remember, these are just integer matrices, and they're determinant 1, so pretty limiting. The parabolic case, these are, you can conjugate these. So you can take a different point of view, pick a different basis, and you can to this matrix right here. And you should recognize, or I want you to notice, that this, from what we described before, this corresponds exactly to Dane twisting. I see. So here we have a lift of the fundamental domain of the torus up in R2. And if we apply, let's just take n equals 1 for the example. That one of these is fixed, so you've got a fixed curve here. And the other one now heads once in its own direction, but once also in the other direction. Now, up to isotopy, I can imagine that what this curve is doing on the original map is instead of going up, it's going that way, and maybe it's going that way like that. So you can really see that it looks like the twist that I drew before. It takes some time to trace a copy of this curve, of the curve you're twisting around, and then it goes its way. All right. So that's a picture of a Dane twist in the case of the torus. Now this is the model after conjugating, but in general, the parabolic element is going to have a fixed direction, which will be some curve PQ. It will correspond to a rational slope. And that's why if you scale it large enough, you're going to have it obviously close up and correspond to a closed curve. So this corresponds to the fixed curve, which is the core curve of the twist. All right. So the more generic picture, of course, is when you have a hyperbolic element. Maybe I'll cycle over. Okay. In that case, your conjugate to, so these have determinant 1. So the eigenvalues are inverse of each other. You've got 2 eigenvector directions. And they're going to correspond to irrational slopes. So maybe you have one direction here, the eigenvector for lambda, and then maybe you have something else. And here, along this, in this direction, you're stretching by your eigenvector, and in this direction, you're shrinking by the same amount. Well, maybe this is double negative, but you're shrinking because this is one of these is going to be bigger than 0, and one of them is less than 0, figuring out the identity. So if you look at what this looks like locally, if you have some evenly spaced slopes that correspond to slopes on the torus, these guys stretched out, and the guys that, these guys should narrow together by a factor of lambda, and these guys shrink. So just trying to just draw a picture of what if it were fibers of a cloth, what it would look like. Okay. So this is really simple to understand. Obviously, it's a linear map on the plane. This has interesting dynamics on the torus. Not going to go into the world of dynamics that much. But the reason why the dynamics turn out to be interesting on the torus is because this is an irrational slope, an irrational direction, actually. So so it's going to keep going. Any one leaf will be calling them leaves already. Any line in one of the fixed directions with those slopes these are just by the virtue of being irrational. These are going to they're going to recur. They're going to come back to any compact place, and they're also going to be dense. I'll just write down that. Well, and recurrent. So you get a chaotic dynamics happening on the torus. Okay. So now the celebrated Nilsen-Thurston classification theorem is describing a similar classification in the very general case where you don't have, it's not known, and it's certainly not, I mean, it's far from known that mapping class groups are linear or anything, so you're not really imagining that you should have any kind of linear structure. But what you have is still a similar kind of trichotomy. So this is Nilsen-Thurston classification. All right. So what it says is that for a mapping class, a general mapping class, one of three things occur, and I'll write it so they're mutually exclusive. There are three types of mapping class, and F is exactly one of these. So there are the finite order mapping classes, like the symmetries that I drew before. You iterate them and you get back to where you started after finitely many steps. Then you have mapping classes that are called reducible, but what that means is, F fixes a finite family of simple closed curves. And finally, the third category is pseudo-Anosov. And I need to take some bit to explain what that means, what that looks like. So maybe I'll put that off for just a minute. So pseudo-Anosov to be defined, and point out a couple of perspectives or ways of interpreting this. First, observe that if your mapping class is, after all, reducible, you may assume that it fixes a family of disjoint curves. Whatever finite family you have to start out with, if they have some intersections, that's okay. Take a regular neighborhood of all of those curves. The regular neighborhood is going to give you a bunch of disjoint curves. So you can assume that the reducible case, they fix disjoint curves. There's only there's a maximum number of these for any given surface. So once you have some of these, in fact, maybe I'll put a little bit more action here. What F has to do then, since it fixes them, is that it has to permute them. And if it permutes them, then if you iterate enough, then it's going to bring them back to where they started. And then you can talk about F on the components of the cut surface. So you can reduce the surface. You cut along the fixed curves. And then you classify again. And so another way to understand this theorem is this is a characterization of the third case, meaning if you're not finite order, sorry, I meant these to be mutually exclusive, so I'm assuming for reducible that you've already excluded finite orderness, so infinite order reducible. So if you're both infinite order and you're not irreducible, then that means that you're this, which means you have a lot of structure. So the point being that pseudo-Anosov curves and pseudo-Anosov mapping classes come with a lot of information for how the mapping class acts on the surface. And also, from this point of view, it tells you that if you want to understand a mapping class, you have to understand pseudo-Anosov behavior. That's what happens. Up to cutting and looking at subsurfaces and permuting and taking a power, this is where you see what the mapping class does. Yeah?
Yeah, I guess I just wanted to go back right here for a sec. Like, I'm not entirely sure when you say any line with one unfixed slope, I just mean when lambda is irrational? Or?
Yeah, but so which it is in the hyperbolic case.
Yeah.
So
That's all. That's what you mean by the one unfixed.
Yeah, I was vacillating between writing it generally and writing it in this example. So parallel to the ones in the example. Thanks. Okay, so what's pseudo-Anosov going to look like? I'll put the definition with me. All right. So I'm going to start with one definition of pseudo-Anosov. And there's all sorts of beautiful characterizations, and I hope to describe a lot of them over the course of these two talks. Okay, so oftentimes, even though a mapping class is a class of the isotopy, I'm picking a particular homeomorphic representative of that class. So in the back of your mind, don't worry if I talk about it. If I act like it's just one homeomorphism, I mean there exists a good representative. And so let's see. Let's call our mapping class F. So for a pseudo-Anosov, a map F, it's going to be associated to a transverse pair of singular foliations. We heard about a kind of foliation of a surface this morning and a certain kind of singularities. This is going to allow different kinds of singularities. It's still going to be a foliation, meaning that away from the singularities, and there'll be only finitely many of them again, it's just going to decompose the surface into one-dimensional leaves, much like all the lines parallel to a given direction foliate the plane. Okay. And there's a pair of them, and they're going to be transverse to each other, meaning any leaf of one intersects leaves of the other transversally away from the singularities. Let's name them. So one is the unstable foliation and stable foliation. And I just put the F there to emphasize these are invariants of the pseudo-Anosov F. And F also is going to have a dilatation, lambda. So what's the role of these foliations? The role is exactly analogous to what happens on the torus case. F is going to stretch the leaves of the unstable foliation by a factor of lambda. and it's going to shrink the other ones. Now, you can't expect this to happen on the surface without singularity, so I'll draw you a picture of what those look like in a minute. You can declare one direction to be a vertical direction and the other direction to be a horizontal direction. Oh, I'm drawing my same picture again, sorry. So here is what happens to the stretched leaves and the shrunk leaves, and of course it's a foliation, it's covering everything, but I'm drawing what happens to evenly spaced leaves. Okay. Such that this happens in local neighborhoods that are away from the singularities. And at the singularities, so in general, I'm thinking about these curves that don't support flat metrics. They're surfaces that support hyperbolic metrics, so I should expect to have, at the singularities, a lot of negative curvature bumping up. So at singularities, I wanted to make the picture. So, just to keep track of who's who. Okay. So what can happen at the singularities? You can have k-pronged singularities for k bigger than or equal to 3. So this is what that would look like. It looks like the grid paper-like looking pieces glued together at a point. So away from the singularity, I still have the foliation by, I guess, blue is my unstable. So this is a 3-pronged singularity. And the other one is supposed to be everywhere transverse. So it has the same singularities, but it comes out transverse. You've got some singular leaves that come right into the singularities, and the normal leaves. So in this case, there aren't closed leaves. These leaves, like those irrational things, they actually go on forever. Even the ones coming out of the singularities, those go on forever. They come back to any, and they have recurrence. They come back to any little, if I make a little transverse arc here and come out here, eventually along any leaf, along the transverse foliation, eventually I'll come back. Is there a question? Yeah?
Do you have any sort of measure of your foliations?
Oh, right. So, so in this case, no, I mean the answer is yes, but I wanted to know if I need that in this context right here. Yes, actually, you're right. This is also defining an xy structure, and you can call one dx and one dy. And you can actually, I said choose one to be horizontal or one to be vertical. You can actually decompose the surface into rectangles, and these rectangles they'll have a notion of length and width up to scaling. So that doesn't matter. Yeah, I'm not sure for this definition right here. I mean,
I guess the point is that it's consistent throughout the whole surface. So there's a
Yeah.
measure that's consistent throughout the whole surface.
That's true. Okay, let me define that. So the measure that's consistent throughout the whole surface is, so let's say that these little these blue ones crossing that tells me my distance dy. If I isotope around this arc in such a way that each point is staying on the same leaf of the foliation, so I move it around, then I want its measured dx to be the same over here. So there is a consistency that goes around. There is a, yeah, these are going to be points in a space of measured foliation up to scaling anyway. So, yeah, you're right. These are measured foliations. Then it makes it less weird what I mean by, then it makes it clear what I mean by stretching and shrinking by lambda. Thank you for clarifying that. So, sorry? Oh, no, you don't. So the condition is on transverse arcs that are, yeah, you don't have to worry about singularities for the condition. If your arc is, you don't have to worry about arcs that are going through one of the singular foliations. I just want this one, as it goes on its merry way, to maintain the same measure, and this one to go on. So this is a condition on the arcs that are away from the singularities. Okay, thank you. Okay, so I'm going to postpone. So there's different ways of so the theorem is that if you outside of these two cases, you get this structure on the surface associated to your mapping class. And with respect to the structure, what your mapping class does is then something that is completely well defined. And the different proofs also give you different points of view on characterizations of this pseudo-Anosov behavior. But what I want to do right now is postpone the proofs for a little bit and actually, I mean, this looks like, oh, great, there's some structure in the mapping class. But just to appreciate what that structure is accounting for, I wanted to actually get into an example, get our hands dirty a bit, obsessing over a particular pseudo-Anosov. So proof postponed. Let's actually, I mean, this is kind of a theoretical description of pseudo-Anosov, but let's see what actually happens. One thing I wanted to point out that I just erased in the hyperbolic case. So you know that you've got this expanding direction and this shrinking direction in the linear map. This is the plain old Anosov case. And you know that any other closed curve is going to be, it doesn't matter, it's going to be some rational direction. It doesn't matter what direction it is. Eventually, the stretching in this direction is going to dominate. So eventually, if you iterate your map on any closed curve, it gets longer. And that's characteristic of a pseudo-Anosov. Certainly, if you're finite order, your curve is going to come back to where it started. Well, OK, reducible, there'll be some curves whose length doesn't change. But the pseudo-Anosov will stretch every curve eventually. Even though it might make a curve shorter temporarily, it'll become longer in the long run for the same reason, because of the stretching direction. OK. But I want to heuristically see that happening in practice. So also, this is in the theme of ICERM enjoying experiments. So this is just a closer look about a particular pseudo-Anosov. So not pseudo-Anosovs, but a pseudo-Anosov. This is going to be, so let's take 3 punctures. You don't lose much thinking of this as a braid. This is really happening on a 4-punctured surface. But the 4th puncture is off on the other side. We're not going to worry about it. Everything's happening here. First, I want to do that braiding half twist with these two. So So this one I'll do first. And this one I'll do second. All right. Okay, and I want to see what happens to a particular curve. All right. I promise you that it's supposed to get longer, but I want to convince you of it. So this is pseudo-Anosov. So let's just take that curve. It goes around those 2 points. And I think what you should try to do is I think you should try to do this faster than me. Okay, so let's do it in 2 steps. Maybe I'll name these so I can keep track. This is following a nice in-depth example in a primary mapping class group, so I'm following their notation. That's a book. Okay. So first I'm doing sigma 2. And then coming down to this column, I'll be the completion of the full map. And then I swap this way. Okay. So this is curve gamma. This is now f of gamma. I want f squared of gamma. I want you to get to drawing f to the f, maybe do it to the at least 3, maybe 4. Okay. I shouldn't cheat. This one first. So it comes up here. That one goes there. This one punched through. I better cheat and make sure I get it right at least. All right. What's next? Gamma inverse. Oh, yeah. Oops. We can do that easily. All right. So now I'm swapping this one and this one. So I've got this one that was here, has now come in here, and is pushed aside this one. And this one originally came from, oh, I could have sworn this was going to be easy. This one came from here, but I also had somebody here. So here we go. All right. Here are the 3 points. You're supposed to do the next one. All right. So it goes here. I'll give you a hint. I'll do the first step for you as soon as the iSerm wakes up. Okay, so there's your first step. So you only have to do this. How? Can you do it quickly? It's not hard, right? Because you're not really, if you're faced with a task, you're not really going to bother with all the lines. You're going to notice that up here I've got 5 strands. And you can keep track of the top 5 and see where they separate out from the the strands around the middle guy, and that's only 3. 3 is not a scary number. So I've got 3 strands here. Of course, these three loop up to be 6. These 5 loop up to be 10. And these 10 are going to come around, and some of them belong to the 6 strands coming from that one, and the leftovers, well, they must go around here. So, and I can even count. Well, that's a little bit harder to see. But let's take the 6 over here, and 4 go out, and they must split around there. So there's 4 here, and 2 here. So all I did was just recopy that picture. But once I've copied that picture in an easier way, then it's not really that hard to do this last step, right? Even though I'm going to cheat and rely on, I've made you suffer long enough already. Oh no, I've made me suffer. Okay, well, I said it shouldn't be too bad, so it better not be, right? So this one comes here. So I've got 3. And 3, I've got this band of 10 that I've punched around. I've got 5 here, and this 4 was still here. So, okay, I messed up. This 3 does not come to this 4. This 3 was the 6 that was coming here. Yeah, and I still had this part. 4, 6. That's these 10 right here. So now I've got 13 here, 5 here, 10 here. And the point of this little excursion is that if pressed, you might invent the bookkeeping notion of train tracks just out of thin air. I mean, what it makes sense to do here is, let's just pinch this, and pinch this, and imagine that maybe I'll leave out my pseudo-Anosovsky story. I've got some weight here, and I've got some weight here, and I've got some weight here, and whatever weight is coming out here, that's this part here that I pinched. Part of it contributes to this guy, and part of it contributes to this guy. And in general, you actually know how you can weight this. So whatever weight I put here, and whatever weight I put here, well, this splits in half over here, this splits in half over here, and these two add up over here, and then they split in half over here. So there really are only 2 variables that I need to keep track of. And then, if I want to know what the pseudo-Anosov does, rather than look at the individual curve, I can just look at what happens to this thing and see where the weights go. And just as a reward for your patience with the other thing, I'm going to do this one a little faster as a cheat. Okay, so that was a one thing I didn't do is I didn't mark which ones were which punctures. But where did y go? So y went here first, and then it went here. So now y is here. Do I have that right? No, that is not right. Yeah. So y is here. And x is the one that went first to here, and then it went over to here. So x is all the way over here. So that's x. And in my picture, x is coming around. And my y strand comes over here. So does the x strand. So these two come together. So this strand right here is the one that's weighted x plus y. And the convenient thing about this is that I can push this back down to the original map. So I know that this goes to so my weight here, I'm trying to do the same thing, is x plus y plus x. So this is 2x plus y. And this one right here, well, this is just x plus y. It just came around unperturbed. And this weight here is whatever the sum of those two things is. So rather than taking the painstaking effort of iterating it, which at least kind of shows that the curve, that this particular curve gets really long, I can see what happens not just to this curve, but to any curve that I can, that is carried by this object which I mentioned, which is a train track. And it's not just the train track, it's, in particular, it's invariant under my map F, because I was able to apply F to the train track itself and push it back down on itself and isotope it back down so that it's the same track again, just by combining some of these leaves. So that's 2x plus y, and this is just x plus y there. All right. So this is, so what happens to the leaves is given by the matrix 2, 1, 1, 1. Y goes to x plus y, and x goes to 2x plus y. So the upshot what are some notes that I wanted to write down? All right. So instead of iterating F, we can see what it does by just applying the matrix. And this will work for any curve that rides on the track in such a way that it's not, for example, backtracking or going. It's riding on the track efficiently. I'll say what that means more carefully in a bit. So that's more than just the curve that we drew. For example, it would work on this curve right here. I could put that on the track as 2 and 0. And then I could see what happened to that under as many iterations as I want. And then I can just draw the picture. I can recover the picture of the image after a while. But this train track doesn't tell me everything. Here's a curve that doesn't ride on the track. At least we know that for any curve on the track, gets longer. Well, in this case, this is a positive matrix, so it's obvious. And but in general, well, never mind general for now. Any curve gets longer. And let's see. OK, so that's the information given by this. What in general is a train track? Yeah?
Why does it not work for the
Oh, So the problem with the one on the right is it's not carried by this particular track. See, if I try to put it here, I could put it, so maybe this is red for don't do. All right. So I could isotope it down, but here I put a kink in it that goes against the tangency of the track. And what I'm taking for granted with this train track is that these really are the weights after I isotope the map. There's not an isotopy that reduces them. That's going to be valid for curves that really do stay tangent to the track the whole time. If the curve takes what's called, if it were a train, this would be an illegal turn, then the weights aren't valid, and I don't know, as I isotope the track, that I'm really having a representative of the curve that's going to have the right number of strands. At the end, I can probably isotope away some of those strands. Okay. So let me get to then what this train track really is recording. All right. So a train track is a graph with more. It's not just the graph. Those it's a graph on the surface where the vertices have tangency information. This tangent information shows which strands join up to run parallel to other strands. The tangencies in the picture imply switch conditions. For example, I mean, there's basically one generic kind of switch. You can have other things, but then you can resolve them. So here we have a switch condition. Whatever number of strands comes in here, and whatever number comes in this way, you better have the sum of them coming this way. That's legitimate. Here, this isn't specifying. Well, this is specifying. This gives a switch condition. Whatever comes out here, comes in here, better be equal to the sum of whatever comes out here. So that's a kind of switch condition. If I resolve it to look like this, then I have a more precise requirement. Okay. So the switch conditions they show you what's legal for what curves are carried on your track. For example, here I have some actual strands coming here, and it's illegal to have them come back out here because then there's 0 coming here. So I'm failing the switch condition if I try to carry the curve like this. Okay. Oh, speaking of carries a curve. Oh, color runs out fast. Okay. For us, actually, I'm content with a loose definition that you can reconstruct the curve from weights on the track. But a track can carry more things. A train track can carry other tracks. And so there's just to give you a little idea of the more careful definition, the train track comes with, so this is a piece of the train track. So you have vertices, and then you have edges, which sometimes I'll call branches. And the point of these is that these should admit weights. The switch conditions are linear relations on the weights. And so here's a piece of an edge right here, locally. And I've got this transverse foliation by like ties of the train track. And what I want to be able to be carried on the train track, so this was what you were asking about, that illegal turn there, is I want to be able to isotope it into the neighborhood, into the ties, so that it's always transverse to the ties. So for example, coming around and doing like that is not allowed. So you can make a careful way of specifying what it means to be carried by the track. So this track was nice for some curves because it told us how the pseudo-Anosov acted on those. Doesn't tell us about other curves. But here's a fact. Given a surface, there exist finitely many train tracks that carry all curves. So if I wanted to record what happened to all the curves, then I can just I can cover all the possible curves with finitely many tracks. Now, not all of those tracks are going to be invariant under my mapping class. So after I look at the image of the track, I might have to use some equivalence moves to relate it to one of the other tracks. So it's you shouldn't so these train tracks are not canonical objects. This choice of finitely many is certainly not canonical. The more accurate way to think about them is that they play the role of coordinate charts, like a choice of basis. In a precise sense, actually, you can patch them together and not only can you describe all curves, you can describe more than just the closed curves. I wanted to give some idea of the and more. Okay. So, I don't know which black pen to trust. Hopefully this one. All right. So, recall that you have branches and you have the switch conditions, which are linear relations on weights. So that means, and actually, I can also assume that my train tracks fill the entire surface, because if I only wanted to use parts of it, I can just I can just weight the branches. I don't use 0. So I can think about a filling train track with weights on it, and if I double the weight and I put the numbers down and then I connect up the strands, then I'll just get 2 copies of simple closed curve, so I don't mind multiple copies. So actually what I can do is I can just normalize the weights. Or I can just think of their projective class. So what I'll get is I will get a projectivized linear space, a little, well, I only, it's going to be cut out by these linear switch conditions. For example, I can't have negative weights. Negative weights don't make sense, so it's like a little patch of, like a little piece of a face of a cone. That's just a triangle. Can't see that picture. But anyway, this is just you can think of this just as a coordinate chart. And since I've normalized as long as I fulfill, as long as I plug in integers that fulfill the conditions, I can always connect it up to draw lots of curves. Since I'm ignoring scaling, all my rational weights correspond to simple closed curves. And the brilliant thing of Thurston's approach to the Nilsen-Thurston classification is seeing that these closed curves, they're like they're rational points in a bigger space. And it's the bigger space, so more generally, you can imagine irrational weights on the track, and that will get you projective measured foliations. There's another way to interpret the non-rational weights on the track, which is by projective measured laminations. But I just want to convey the idea that if you generalize what's carried on this track and you look at all the points, then you have a bigger space. And it's on this whole space, which will turn out to be the sphere and a boundary of another important space. The mapping class group will act on this space. In the special case of the pseudo-Anosov, it's going to have fixed points, which are going to be its source and its sink. And those fixed points are going to be projective measured foliations. If you fixed a curve, then you would be fixing one of the rational points. And then you'd be reducible. The pseudo-Anosov case corresponds to fixing these, having a source and a sink in this space right here. So I wanted to go back to our particular example. Oh, thank you. All right. So this curve right here, there's a special it's got a positive eigenvector. Well, I'll just write down the number, but this is just a particular, this is a famous, nice example. Sorry, that's a fraction on top. And if I can just imagine weighting these branches with these values instead of integer values, so somehow this irrational worth number of strands, 1 plus point square root of 5 over 2 strands goes through here, and somehow a measure of 1's worth of strands goes through here. Then when I apply the pseudo-Anosov, well, it's the eigenvector, so this is going to be scaled by the same amount, and this is going to be scaled by the same amount. But if I decided from the beginning that I'm going to normalize and I don't care about the particular values, I just care about the weighted values, then since I've scaled it, I've only scaled it, I haven't changed. So this eigenvector here is going to correspond to a fixed point in this larger space. So that stands for projective measured foliations. And so what do I imagine that that looks like? Well, let's draw the track again as bands. So here's a band right here that splits off into, some of it goes here, and some of it goes here. And then this band splits into two and comes back around to itself. And this splits into two. And so what I'm saying is invariant is if I weight this by 1, and if I weight this by the other value, now, these are just rectangles. I've given them height, so now I've got a measure on them, and I've got a measure. I've got that kind of transverse measure that I was talking about before. All of the vertical, the horizontal directions foliating that rectangle. Well, there's a natural notion of a measure if I go transversely to them, which is just how far down did I go in the width. So I'm poofing out the train track to become a foliation that's then carrying, and then I'm placing the measure on it up to scaling. So I'm putting a measure class on it, and this thing right here, this is another view of that structure that's invariant on the surface. So this is, in particular, this is the unstable foliation, because these leaves right here, these are getting longer. Okay, and I promised you transverse foliations. Yeah. Okay, so the surface is actually, and for this too, this is a 4-punctured sphere. So there's one more point. So there's a puncture here, a puncture here, a puncture here. Actually, let me color these punctures. That's going to be useful in a second. Oh, that's a good point. There was a second kind of singularity that I needed to describe. These punctures are a certain kind of singularity that's only allowed at punctures that I didn't bring up before. Before I said that you're allowed to have these k-pronged singularities. There's an additional kind of singularity only allowed at punctures, and this is a 1-pronged singularity, so this has to be a puncture. Here's a foliation, here's a singular leaf coming out of it. And here's the transverse foliation. And here's its singular leaves coming out of that. So there's going to be a transverse foliation to this too somehow. And I found that hard to see. So then I got my hands dirty and computed it to see what it could look like. So I can understand, after seeing this description and expecting to see, I mentioned how you could actually decompose the surface into rectangles, and this is supposed to be a 4-punctured sphere, and this is not telling me how I'm going to decompose that into rectangles. Obviously, I've got 3 rectangles at least here. It so happened that in a way, the structure on this one is easy to find because this turns out to be not that far from an honest, true Anosov map. If you take the 2-1-1 map just on the torus itself, so you have the torus, and it kind of goes back to that exercise that I hinted earlier, and you can take the quotient by the hyperelliptic involution. There are -1 somewhere. Like that. The one that rotates it this way. 1, 0 goes to 0, 1, and 0, 1 goes to -1, 0. Yeah. Wait, no, that's not enough. One more time. What is it?
Just minus like 82.
Sorry?
I think you just minus 82.
Oh, yeah. Right? Yeah, okay. Of course, that's order 2. That's clearly order 2. So this 2-1-1 map is going to descend here, and here, this is the 4-punctured sphere, and I'm only looking 3 of them. I put 1 in the back, and so I thought, oh, we can see the flat structure. We can actually construct it. So something I haven't figured out, though, is that I am, there's some choices that I made that made me backwards, a mirror view. So I'm going to flip it in a second so you can see how you can superimpose it to here. And let me be consistent with who the with which ones correspond to which branch points. So from the other direction, if you know your foliation, so in the torus case, I know the 2-1-1 foliation, then I can actually find a rectangle decomposition by a procedure that's finding a Markov decomposition, it's called, where I take some arc that's transverse to the stretching direction, and then I follow along leaves, confident that I'm going to at some point return back to my arc. And then I do that, and I extend my arc as far back as I can, I mean as wide as I can until I repeat. So there's a well-known picture for the 2-1-1 map. Let's see, this is not going to be completely accurate, but here's a good, turns out this is a good transverse arc to take. So I want to, let's see. So this is going to be maybe somewhere here. Oh, this is it. So I have this rectangle decomposition here, and I can actually, on the torus, see what happens, see the dynamics of this without too much trouble. Let's see. This is the blue square. This is a red square. If I patch these together, I've got this bigger red square and this smaller blue square, or rectangle, sorry. And what the map does, at the risk of squeezing it in, well, this one shrinks, it stretches in the stretching direction and it shrinks in the shrinking direction, so it becomes this long thing that runs over, let's see. Yeah, it runs down the middle, I think. I didn't write that down, of the red one, and the red one, meanwhile, runs through part of this, and then it runs. So this part is fixed right here. You can work it out just by applying the map to the squares, but you can actually get a discrete picture of the dynamics this way, and you can iterate this. Okay. So anyway, I'm glossing over these details because that's and how I'm going to actually prove this is I'm not going to use this point of view for proving it. I'm going to use the the Teichmüller space Baerstock point of view. It's the most elegant and fastest way to do the proof. But there are so many other points of view. So I wanted to show some of them. The rectangle decomposition corresponds to a Markov position of the surface. You can do that in the general case, although it's more complicated. I've tried to do that with the four-punctured sphere by simply noting the fact that I have an identification with the hyperelliptic involution. And so this picture right here is almost this picture right here. It's almost because I made some choices, so you have to I got a mirror image of what was going on here. But you see the track there now. That green train track there is exactly this track here. We've got the tangency here splitting in two directions, one that both add to the one on the left. And so that's why I color-coded the singular points, so you can see which branches they correspond to. And you can go the other way around. If you start off having a rectangle decomposition of how your map acts, you can make edges corresponding to the rectangles, and then you will have to figure out how to connect those to make a track by creating additional branches that respect possible turns that should be legal directions in which a foliation might stretch. So here, for example, if you were to construct a track that corresponded to this foliation, to this measured foliation here, I would add this branch here, since from this square I can go from here to here. So the rough idea behind that is that I've got this combinatorial tool of train tracks that I can use to keep track of measured foliations, which I can expand, or I can follow to find a rectangle decomposition of the surface. And then you can go from any one of them. You can start with the rectangle decomposition, and you can construct the track. That's what I was trying to give an idea of here. More precisely, you identify the unstable leaves, so those all become points. And then you have to make decisions at the switches. So you can go back and forth between these points of view, and here I'll just explain the colors a little bit. This is the image of the train track under that pseudo-Anosov, and you can see that I have something wrapping around y and something wrapping around x. The color there, the blue part, is the image of the square that's around the blue. So you see that is wrapping around the y. The red part, the part that's colored red, is the square that's adjacent to the red puncture, which is playing the role of a singularity. The black is the fourth puncture, and that's also singularity. And these are these one-prong singularities. Let me draw you. There's identification. So that right there, that's a fundamental, that glues up to be the four-punctured sphere. I didn't write all the identifications, but the train track evidences some of them. So this one-prong singularity, from the point of view of the rectangle structure, in practice it looks like this. So let's see. Maybe I cut along here, and I've got, so that's the singularity, and here is one foliation, and here's the other, and this is certainly now a transverse foliation. And this is what's happening. This is the foliation that you have at each of those three punctures there, and even this one too. Although the identification might, well, it's a little bit more complicated in a neighborhood there, maybe. So this you glue to this. So this glues up to be a four-punctured sphere. And those three rectangles there, those three rectangles are the rectangle decomposition of the four-punctured sphere. Okay, so are there other questions? So I apologize, I'm probably waving my hands a lot. This is just a literal hands-dirty example to see some of the tools that that describe that describe pseudo-Anosovs here, but I'm hinting at some kind of space where the action of the mapping class group is important. Tomorrow, I'll tell you the proof of the classification theorem. It's using Teichmüller space, and so there's Beers's point of view is this nice point of view using that complex analytic side of things, and it comes out to be a very elegant proof. So I'll do that proof with nice definitions and much less hand-waving, and then hopefully after that I'll have some time to squeeze in some hand-waving of the parts in that proof that correspond to these other kinds of structures that Thurston was using when he came up with this way of classifying elements of the mapping class group. The story is that he had this complicated proof of it when he first gave it to the audience, and Beers was in the audience, and he said, "Oh, there's an easier way to do that." So that proof is shorter, and it's not necessary to use this machinery. I'll try to point to how the machinery relates after that. Nilsen also, it turned out that within Nilsen's work, the elements for the proof of the theorem were already all there, but people didn't understand them, or people didn't know it was there or see how it all came together until Thurston's investigation of the story. So, thank you for today.
This eigenvector was with respect to this particular train track.
Yes.
But so is the point that curves that are carried by all of the other finitely many train tracks eventually go to this train track as well?
Oh, that's true. This is an attracting fixed point. So you start off maybe on other. So the other train tracks, you can think of them. They're coordinate charts for this space which contains all possible projective measured foliations, and the map is actually going to, the mapping class F is going to act on this space, and it's going to have one point be a source and one point be a sink. Those are corresponding to the two foliations. The other ones, wherever they are, whatever chart they're in, they're going to gravitate towards one. So any curve in the surface, even that might not be carried by this track, if I iterate enough, it actually will be eventually carried by this track, because it'll start approximating the measured foliation that corresponds to the irrational weights on the track.
How do you find that? I mean, you just handed some pseudo-Anosov.
Yeah, no, that's a wonderful question. For example, there's another proof, which I don't know how much I'll get to say anything about, of the Nilsen-Thurston classification, and the proof goes by finding the train track. This is the algorithm of Vespina and Handel. It's actually coming from a more general point of view. Outer automorphisms of the free group, these are acting on graphs. And so on a graph, there's in some ways a simpler, it's just a graph, so there's like a cleaner notion of what's a train track with legal paths there. And they have an algorithm for finding train tracks and improving them until they become the one that optimizes, that really shows the dynamics of the map, and then converting that track to one of the Thurston-style train tracks. So there is an algorithm for finding the train track. Otherwise, you have other theoretically, you know that there exists the rectangle decomposition. And then there's a method, given the rectangle decomposition, to construct the track, which is, which I tried to hint at here. I mean, there's long branches for the length of the rectangle. And then to go between rectangles, you have to add so-called infinitesimal branches, and you have to figure out where those need to go. But some of it is, I'm not good at all the parts of it nearly, but there are dictionaries between all these point of views. Some dictionaries are harder than others. But I find that a fascinating thing about the topic. Yeah?
Simple question. So what is the true track of the other polynomial?
Of the which one?
So you have
the other direction. Yeah. So a train track for that. I should also emphasize, I mean, that there's nothing, you can do these equivalence moves on tracks. So, don't think that the train track is the canonical thing. But once you put weights on the train track and you get the measure foliation, that's the invariant. That's the invariant of the pseudo-Anosov. The train track is like a coordinate system that allows you to see it. But a train track for the other one, I think, so this is actually, I mean, this is a fun example. This example is so parts of this example are done at length in this title is something like this. This is in the title. But this is an example that you can really get your hands dirty with, and you can actually find there all of the tracks. There are actually in the four-punctured sphere there are just 4 tracks that carry all curves. You can see how they create this space, projected measured foliations. It's just going to be 4 lines together to make a little square circle topologically. And you'll have the attracting point, and you'll have the repelling point, and I think it's carried by this track right here. But it boggled my mind to be able to put them together to see how they're transverse to each other until I just tried to play with the actual actual linear map to find the foliation where they're transverse. So you don't see that. I mean, you can check that as an exercise. See if you can really understand this example. If not in the torus, I mean, at least in the torus case, but then descending to the 4-punctured sphere case and see the source and the sink train tracks and corresponding foliations. Yeah, I find it a fun example just to obsess over and get your hands dirty. But more elegant stuff planned for tomorrow, the actual proof, or one of the many beautiful proofs.